All right, section 2.8, let's get into it with probability. Just to kind of give you a preview here, we're going to be talking about three distinct topics, okay? The first one is going to deal with probability, and there are two types of probability. There's theoretical probability, and there's experimental probability. After our discussion of probability, we will move on to odds. And odds is more of a comparison. It's more of a different system. So you'll have theoretical probability, experimental probability, and odds. And your goal for all of this is to be able to understand the difference of all three of those. Okay, so let's do some quick definitions. And if you don't remember a lot about probability, you probably want to pause this and read it all to yourself. I'm not going to go through all of it. It does say the probability of an event is a measure of the likelihood that the event will occur. So probability is synonymous with chance. What is the chance something will happen? What is the likelihood something will happen? It is a number between 0 and 1 inclusive. In other words, it's a number in between 0 and 1 that also includes 0 and 1. So if we think about all of that real estate on the number line between 0 and 1, numbers like 1/2, 1/3, 2/3, 3/4, those could be probabilities. 0 could also be a probability. If something has a probability of 0, what does that mean? Well, that means it's impossible. It has 0% chance, 0 out of whatever, 0% chance that that event will occur. It's kind of like me saying, what's the probability that next year we'll have 14 months? It's a 0. It's not going to happen. Okay? Or you could have a probability of 1. And probability of 1 means that it's a sure thing. It's definitely going to happen. Okay? Tomorrow is a day that will end in the letters D-A-Y. Okay? That's a 100% chance. It's a probability of 1. Okay? It's a sure thing. It's definitely going to happen. Okay? Go ahead and read these. If you're not as familiar with probability, feel free to pause and go over those. But I do want to give you a quick definition for theoretical probability, which is the first type we will discuss. All of these things relate to theoretical probability. So let's go ahead and get this down. Theoretical probability. And what do we mean by theoretical? It's kind of like armchair probability. You can just sit around and think about it. You don't have to conduct any experiments or take any, real life data. All of the answers are achieved by thought and reason. Okay, that's theoretical probability. And to do theoretical probability, we're basically going to use the number of favorable outcomes. It's going to be your numerator over the total number of possible outcomes. And we'll use a quarter as an example. So let's imagine that you want to know the probability of flipping a quarter and it landing on heads. You don't actually have to have the quarter to come up with an answer. You're going to theorize what that might be. Okay? How many possibilities do you have? Right? Well, it could land on heads. It could land on tails. So your denominator, right, the bottom part, would be a 2. That's the total number of possible outcomes. Okay. Now, for the numerator, what's the number of favorable outcomes? Well, what do you want to receive? You want to receive, okay, you want to land on heads. So you have 1 out of 2 probability for it landing on heads. Okay. And also a 1 out of 2 probability for it landing on tails. And you don't even have to flip the coin. You can just theorize it. So that's an example of theoretical probability. Total number of favorable outcomes over total number of possible outcomes. All right, let's apply this. And you might want to use your pencil and paper at this point just to jot down your answer before I go over it. Here's an example of theoretical probability. In a group of students, 12 ride the bus to school, 8 are driven to school, and 5 walk. One of the students is chosen at random from the group. What is the probability P that the student walks to school? All right, let's go over some notation really quickly. When we talk about probability, we do use a capital letter P. So if I were to ask you this question, okay, what's the probability of randomly selecting a student who walks? I'm going to write down a P for probability, and then in parentheses I'm going to put a descriptor of what my favorable outcome is that I'm looking for. Well, I want to know the probability of choosing somebody who's a walker. So I might use the verb walk in here. Probability that the student walks. Okay, I want you to go ahead and try that on your own. Remember, theoretical probability is number of favorable outcomes over total number of possible outcomes. Go ahead and answer this on your own. Hit pause if you need to, and then we'll go over the answer together. Okay, what'd you come up with? I usually like to start with the denominator myself. Okay, so if I'm talking about the total number of possible outcomes, well, in this situation, it's the total number of students we're considering. So I've got 8 driven, 12 who ride, 5 who walk. I add all of those up. I've got 25 possibilities, 25 students to choose from. Okay, out of those 25, how many walk? Well, that's pretty easy. 5 out of 25 walk. So that's your answer. The only other thing you have to do is you do need to reduce your fractions with probability. Okay, so what would you divide both of these by? Divide them by 5, and you're going to get a 1 out of 5 chance, or a 1 out of 5 probability. Pretty easy. Okay, let's try some more examples. Definitely going to need your pencil and paper here. You should already have that out. Now we're going to go back to using a 6-sided die, which if you read the stuff on the opening slide, we brought up the 6-sided die. You know, if you have 2 of these guys, you call them dice. You got 1 of these guys, you just call it a die. I'm going to attempt to draw one here really quickly. Not the best artist in the world, but it'll work. Okay, let's see. Nice. Kind of proud of that. All right. So I want you to find these probabilities on your own. Rolling a 6-sided die, I'd like to know the probability of rolling an even number. Then I'd like to know the probability of rolling an odd number. Then the probability of rolling a 4. The probability of rolling a prime number. The probability of rolling a 7. And then the probability of rolling a number. Okay, so go ahead and think about those. Do this theoretically. And then we'll reconvene to go over answers. Go ahead and hit pause now. All right, let's talk about the probability of rolling an even number. You have 6 possibilities. So you're going to have a denominator of 6 here. What are the even numbers that you could roll? Well, you could roll a 2, you could roll a 4, you could roll a 6, right? So out of 6 possible numbers to get, 3 of them are even numbers. Okay, so you have a 3 out of 6 chance. Now that number does need to be reduced. Divide both of those by 3, and so you have a 1 out of 2 or a 1/2 chance of getting an even number. Okay, let's go to the odd numbers. Okay, you could roll a 1, a 3, or a 5. So out of 6 possibilities, 3 of them are also odd. That just makes sense. And that also reduces to 1/2. Probability of rolling a 4. Well, out of your 6 possibilities, 1 of them is a 4. And that can't be reduced. So you're already there. The prime number is the tricky one. Okay? What constitutes a prime number? Well, by definition, a prime number is a number whose only factors are 1 and itself. To be a prime number, though, you have to have at least 2 factors. So if you thought that the number 1 was a prime number, it's not. You have to have at least 2 factors to play the game. The first prime number is actually 2. The next prime number is 3, because the only factors are 1 times 2 or 1 times 3. And then the next prime number is 5. Okay, so out of 6 possibilities, 3 are prime numbers. And that one also reduces to 1 out of 2. All right, you got a 6-sided die. What's the probability of rolling a 7? Well, that's an impossibility. It's not going to happen. So the best answer here is 0. Remember, probability exists between 0 and 1 inclusive. So you can use a number like 0 for your answer. You could also express this as a decimal, 0.0, or a percent, 0%. The fraction version, technically, for this would be 0 out of 6, because we have 6 possibilities, right? So you could also write it as a fraction, 0 out of 6, and that would be fine. All right, what's the probability of rolling a number? Okay, the die is not going to land on its like a corner in a funky fashion or anything like that. It's going to land on a number. We're definitely going to get a number, so the best answer here is 1. Okay, you could also express that as a decimal, 1.00, right? As a fraction, this is 6 out of 6. Out of 6 possibilities, 6 are numbers. So these two right here are actually both considered the fraction form, right? Or the decimal form, either way. As a percent, what are all of these? Well, 100%. These are all equivalent answers, and all of them are just fine. All right, I hope you did well on that. Let's move on to something else. So that was theoretical probability. Let's take a look at experimental probability, okay? In experimental probability, you're actually going to perform the experiment. If you have the coin, you're going to flip it, okay, and do several trials to see how many times it lands on heads or how many times it lands on tails. If you have the die, you're actually going to roll it, and you're going to roll it over and over again. You're going to do several repeated trials and then analyze what you come up with. So sort of the formula for experimental probability is this. It's the number of favorable outcomes observed. Okay, so how many times you actually see it land on heads, for example, over the total number of trials. And maybe I'll write in total right here, just because that emphasizes a total. Okay, so your definition for experimental probability deals with trials and actual observed favorable outcomes. Okay, let's do an example of this. So imagine that you work at an ice cream store. Okay, you're the only employee. Maybe it's a summertime job. It's kind of boring. You actually don't get a lot of business. So you start playing this game with yourself where you're going to try to predict what the next customer who comes in is going to order. Okay, you only sell 3 flavors today. So you can see the vanilla, the chocolate, and the strawberry. And you start taking track of what your customers have been ordering. And so you're going to use a tally mark system throughout the day to just keep track of what everyone's getting. In an experimental probability, you actually use this kind of knowledge. You use your knowledge of the past to sort of predict the future. Okay, so this is what your customers have ordered. And I want you to use this data. So every time a customer orders something, that's like a trial. Customer comes in, says he wants a strawberry ice cream cone. Okay, that's one of your trials. Boom, I put a tally mark for strawberry. So here's where I'm at. Maybe it's 2 o'clock in the afternoon. These are, the results of what my customers have ordered. Now I'm waiting for the next person to come through the door, and I already want to have a prediction based on the past of what this guy is going to order. So what's the probability that the next customer will order chocolate? What's the probability that the next customer will order not chocolate? What's the probability that the next customer will order strawberry? What's the probability he or she will order mint chocolate chip? What's the probability he or she will order ice cream? Okay, and if you're not sure how to proceed, go back to that formula, that definition for experimental probability. Total number of favorable outcomes observed over the total number of trials. I want you to try that on your own first. Take your time. Go ahead and hit pause now, and then we'll reconvene to go over answers. All right, let's look at probability of chocolate. And I'm going to start with the denominator here. It's the most important number. How do we arrive at the total number of trials? Well, we're going to add up all of the vanilla orders plus the chocolate orders plus the strawberry orders. So that looks like 21 vanilla, 14 chocolate, and 7 strawberry, right? And if I add all of that up, I believe I get 42. So I've done 42 trials so far. Out of those 42 trials, okay, how many in the past have ordered chocolate? Well, count up the chocolate. That's 14. That's actually the probability I'm going to use for the next person who comes in. They have a 14 out of 42 chance, according to prior history, of ordering chocolate. So that is my probability. All I have to do now is reduce my numbers. What can I divide those by? Well, I think I can divide them by 2. I can also divide them by 7. Let me start with 7. Divide by 7, I get 2 over 6. Oh, I could have divided them by 14, because now I can keep going. All right, so I can also keep going, divide by 2, divide by 2. Looks like I get a 1 out of 3 chance, 1 out of 3 probability. Okay, I could have divided those by 14 now that I look back at it. All right, probability of not chocolate. Let's see how you did on this one. We're also going to use that 42 as a denominator. How many of these things are not chocolate? Well, that's really another way of saying vanilla plus strawberry. So 21 plus 7, it's going to be 28 out of 42. Okay, now I can divide those by 14. And if you don't see that, you could have divided them by 7 and then something after that. But I'm going to get 2 out of 3. And that kind of makes sense. You know, chocolate plus not chocolate should add up to 100%, or should add up to a 1. So those two numbers, 1/3 and 2/3, kind of support each other. All right, what's the probability of ordering strawberry? All right, out of 42 so far, 7 people have ordered strawberry. Now, can I reduce that number? Yes, I can divide both top and bottom by 7. I'm going to get 1 out of 6. Okay, and here are some more of your theoretical questions for experimental probability, I guess. What's the probability that the next person is going to order a mint chocolate chip? Well, it's not an option. So what's your only recourse here? 0. It's impossible. Not going to happen. What's the probability that your next customer orders ice cream? Well, those are the only 3 things on the menu. And we're not talking about coming in and asking for a cup of water. Paying customer is going to pick either vanilla, chocolate, or strawberry. They're all ice creams. So that's a 1, or a 1.0, or a 100% chance, however you want to say it. All right, that's experimental probability. Very good. Now let's move on to odds. Okay, odds is a different system. Odds is more of a comparison. Okay, it says odds is the number of favorable outcomes to the number of unfavorable outcomes. And I want you to notice, this is the confusing thing about odds. That is a fraction bar, but I'm never going to pronounce it as out of. When I read the fraction bar, I actually want to say the word to. I'm comparing favorable outcomes to unfavorable outcomes. And if you want to make this even more clearer, I guess, I like to use the horizontal system. Okay, odds is going to be favorable versus, and we're going to use a colon pronounced as to, but it means versus, unfavorable. It's kind of what you want versus what you don't want. What you want to what you don't want. Those will give you the odds. All right, let's look at an example. It says, you randomly choose a letter from the word summer. What are the odds that the letter is a vowel? Okay, so try to get probability out of your head right now, as we're talking about odds. And remember, odds is going to be favorable to unfavorable. Now, if we were talking about probability, we'd probably want to know the number of letters. There's a total number of 6 letters. That would be our denominator for probability. 6 would be a very important number in the probability problem. But for odds, you're not going to see that 6 in there, not readily. Okay, it's favorable versus unfavorable. So we're looking for vowels. Those are the favorable. How many vowels do I see in summer? Well, I've got the U, I've got the E, so it looks like 2. So I have 2 vowels. To how many unfavorable outcomes? Well, the unfavorable are going to be the non-vowels, right? So how many non-vowels, or in other words, how many consonants do we have? We have 1, 2, 3, 4. The S, the M, and the R. So 4 of these guys are unfavorable. And that's your odds right there, 2 to 4. Those are your odds. Notice, if I add those two numbers together, I do get the total number 6. Okay, so the 6 is still kind of there, it's just hidden. 2 of them are like winners and 4 of them are like losers, so to speak. But they do add up to a total number of 6. Now you do need to reduce your odds. Okay, so what could I divide both of these by? Well, I could divide them by 2. So this would simplify to 1 to 2 odds. So just like probability, you are going to reduce your odds if you can. Okay, I want you to try these 2 on your own. Example 3, pencil and paper. I want you to tell me the odds of getting an S and the odds of getting an M. Go ahead and try those on your own first. Hit pause now. All right, let's take a look at the odds of getting an S. So back up there on summer, I've got 1 S. So favorable outcomes is going to be 1. Okay. Unfavorable outcomes will be all the letters that are not S's. And I have 5 of those. So it's a 1 to 5 odds. And I can't really reduce that. So that stays as 1 to 5. Notice the probability would be 1 out of 6. So a probability 1 out of 6 is really 1 to 5 odds. 1 that's a winner, 5 that are losers. Okay, let's move on to the next one. What would be the odds of receiving an M? Okay, well, let's go back up to summer. How many M's do I have? Got 1, 2 M's. Okay, so I have 2 favorable, and the leftovers are unfavorable, so the other 4 are unfavorable. So that's my answer, 2 to 4 odds. Once again, this can be reduced. I can divide both numbers by 2, and I end up getting 1 to 2 odds. All right, very good. All right, you're going to try this next one on your own. This is a little bit more challenging of a problem. It says the probability of winning free medium fries in the McDonald's Monopoly game is 0.16. What are the odds of winning free fries? And I want you to use that probability. Now that probability is given to you as a decimal. Don't let that throw you. It's got a probability of 0.16. How do we take a number like that and maybe convert it into odds? I want you to try that on your own. Go ahead and hit pause now, and then we'll reconvene to go over answers. All right, let's see what we came up with. First issue is that decimal, right? Some of you guys might not like that this was given to you as 0.16. Well, what does that mean? Well, in probability, often we're very comfortable with the fraction, so let's just convert this to a fraction. How do we convert a number like 0.16 into a fraction? Well, remember, this is pronounced 16 100ths, right? Because it goes all the way out to the 100th place. So maybe it would serve us well to rewrite this as 16 100ths. And then probability-wise, we kind of think of that as 16 out of 100. So if we imagine that we play this game 100 times, you get 100 of those little Monopoly tickets. Out of 100, 16 of them are going to win you fries. That's what the probability teaches us. Well, let's just change that over to odds. Okay, remember odds, once again, is favorable versus, favorable versus, or favorable to, unfavorable. What's the favorable aspect here? Well, winning is favorable. So out of that 100, right, 16 of those tickets are going to be favorable. How many would be unfavorable? Well, that's really the trick here, right? How do you figure out If 16 are going to be winners, how many are going to be losers? We'll go back to that total of 100, right? If you imagine playing 100 times, if you win 16 times, then the times that you don't win, those are the times that you lose. You need to do simple subtraction there. Subtract your wins, you end up with your losses. Okay, so you're going to lose 84 times. Or at least, at the very least, you're not going to win fries 84 times. So 16 to 84. Those are your odds. Okay. Now, you can reduce this, so let's do that. I think I can divide both of these by 4. So 16 divided by 4 is 4, and 84 divided by 4 is 21. So you end up with 4 to 21 odds, and you do need to have that reduced to receive credit. Okay, so that's converting odds to probability, and you should be able to go back and forth between those two systems. Okay. Here we are going to try going from odds to probability. So it says you play a card game where the odds of winning to losing are 2 to 3. Those are the odds, 2 to 3 odds of winning to losing. All right, I want you to answer these two on your own. What's the probability you will win? What's the probability you will lose? Go ahead and hit pause now, and then we'll reconvene to go over answers. Okay, it tells you that the odds are 2 to 3. So for every 2 times you win, right, for every 2 times you win, you lose 3 times. So like in a theoretical universe, it sounds like you're playing this game 5 times. And of those 5 times, you're going to win twice and you're going to lose 3 times. So that 5, when you add these two numbers together, you add those two numbers together, that's going to give your probability, that's going to give you your probability total. You're going to imagine that you're playing a total of 5 times. Out of those 5 times, how many would you win? You'd win twice. Out of those 5 times, how many would you lose? You'd lose 3 times. And this is actually a really great way of seeing how the two systems go back and forth. That total of 5 is expressed when you see the reduced odds here of 2 and 3. You can just add those up to get your denominator for a probability problem. But I want you to understand why. Okay, 2 wins and 3 losses equals 5 total times playing the game. That's where we're getting the total of 5 down there. Okay, so 2/5 and 3/5. Last one, it's kind of a challenge. All right, you're going to Las Vegas. You're standing at 2 different games. One of them advertises a 3 to 5 odds of winning, and the other one advertises a 1 out of 2 chance, or a 1 out of 2 probability. Okay, which would be the better game to play? Which one do you have a better chance of winning at? Okay, I want you to think about that and come up with your own answer and a defense of your own answer, and then we'll talk about if you're right or wrong. So go ahead and pause now, and then we'll reconvene to go over the right answer. All right, let's cut to the chase. This guy is your winner. Okay, so the game that has a 1/2 chance of winning, that's going to be the one you want to play. Why? All right, well, let's do some conversions here. It's kind of hard to compare odds to probability, so let's try to get them both in the same system, right? If I want to take this 3 to 5 odds, and maybe I should turn it into probability. So if I win 3 times and lose 5 times, it sounds like I'm playing a total of 8 times. Okay, and out of those 8 times, I'm going to win 3 times. So that's actually my probability of winning, right? I have a probability, 3 out of 8 probability of winning for the first game. Now the second game, it says I have a 1 out of 2 probability of winning. So the question is, can we compare these numbers now? A 3 out of 8 probability versus a 1 out of 2 probability. And the best way to compare those, well, one, just say, well, which number is the bigger number? That's your winner. Okay, and some of us look at that and we know it's 1/2. But if you're not sure, maybe you can convert 1/2 into eighths, right? How many eighths is 1/2? Well, it's 4 out of 8. And when we compare 3 out of 8 versus 4 out of 8, it's no contest. This guy's going to win every time. Okay, so this is your winner, the 1 out of 2 probability game. All right, I know there's a little bit longer of a lesson tonight, but hopefully you have a better understanding of theoretical probability, experimental probability, and odds, and you are going to need to know all of this stuff. So good job. We've reached the end of Unit 2. Remember, we covered a lot of ground, adding and subtracting real numbers, dividing real numbers, multiplying real numbers, multiplication rules involving negatives, involving multiple negatives, involving exponents, how to add and subtract matrices, and then also some probability and odds. So you have a lot to study. Feel free to fast forward back through the videos and kind of pause for the parts that you need to practice on. I would go through every video again, maybe and fast forward, but making sure that I understand what's going on, that I can predict all the right answers, and I have a firm grasp of all this stuff. I want everyone to try to get an A on this next test. All right, good job.